So far, we've discovered that there are forces of attraction within a molecule, and we've identified these as ionic, covalent. Now, I've also mixed metallic in here. We haven't discussed this in this course, and that's not a problem. So we're really focused on ionic and covalent, with metallic being the strongest one. You know, if a group of metals are put together, ionic would be next in terms of boiling point, and covalent would be our third one. So what we are interested in here is forces within molecules are called intramolecular forces. And those are the ones that we've just kind of previously discussed. So molecules where electrons are not shared equally, so definitely in an ionic bond where you have a positive and you have a negative, the electrons are getting pulled towards the negative end. And we have also discussed polar covalent. That's where you have a covalent bond, perhaps even like water. And what's happening in the bond, according to our electronegativity, is the electrons are getting pulled up towards the top. So you end up getting a positive and a negative end within the water molecule. That's a dipole. We're going to be discussing that here. So in this bond inside of our water molecule, that bond there in particular, the electrons are moving up towards the oxygen, so it becomes negative, and that leaves the hydrogen end positive. And this is what we're going to be investigating here, and this is called intramolecular forces. Now, there's an opposite, and the names are quite similar. Forces between molecules are called intermolecular forces. This is what we're going to be investigating now. So we've already done intra, we just didn't name it as intra, but now we're doing intermolecular forces. A way I remember this, and it's not a great one if you're not a sports fan, but in baseball, when the two leagues play against each other, it's called interleague play. So the leagues are playing, there's games between the two leagues, between. It comes up a lot in science if you can remember it. I know that's not the easiest thing to remember. So there are three types of intermolecular forces. And really when it comes down to it, every liquid you can produce falls into the category of either being a polar liquid or a non-polar liquid. We're going to learn more about these coming up too here. This third one, called hydrogen bonding, is just like a bonus force that is associated with a polar molecule. So again, any liquid you find can be classified as polar or non-polar, and then some of the ones that are polar also have this extra bonus force. So let's talk more about polar molecules. These are covalently bonded compounds that are in the liquid state that have a dipole. What does it mean to have a dipole? So let's recall that electronegativity, this was on your periodic tables in the fourth trend, determines how electrons are shared within a covalent bond. Sometimes they can be shared equally, and sometimes they are not shared equally, and that's what we're interested in for polar molecules. So let's take a look at water right here. So if you look up the electronegativities, you've got oxygen up here at about 3.4, and you've got hydrogens on each end at 2.2. The electrons are simply going to migrate towards the bigger number. So in both bonds here, electrons are actually moving towards the oxygen. So what that does is it causes us to have an oxygen that ends up being a bit negative here, slightly negative, and you've got a couple of hydrogens that both end up being slightly positive. And so what we've discovered here is that this molecule has a dipole, and the dipole would point up. The dipole just simply points to the negative end, and you cross it there. It looks like a little plus sign. So if a dipole pointing up, that means it's polar. So all polar molecules will thus have attractive forces for other polar molecules. They must. If we've got positive and negative ends of molecules, they have to be attracted to each other. This is why you can overfill a glass of water. It's like the water molecules are kind of hanging onto each other. They're not letting ones fall over the edge, so that's why you can have a meniscus. And the other thing we have to remember is that polar molecules lack symmetry. If you were to grab this water molecule in your hand, you could definitely tell if you were holding it, say, by the blue part or the green part, and you moved it around, you could see a difference in your hand. That's going to be different for non-polar molecules. So let's discuss non-polar molecules. They're essentially kind of the opposite. So again, they're covalent compounds, liquid state. This time they have no dipole. So let's take a look at a molecule. This one here, if you were to draw in each bond, you would have electrons moving towards the chlorines. The only problem is that it's all equal in every different direction. There isn't one end for me to draw or one direction for me to draw a big overall dipole arrow, because everything cancels out. It's symmetrical. You grab this in your hand, you wouldn't be able to tell which way you were holding it as you turned it around. It would just look exactly the same. And even same for this molecule here. Again, there's no overall arrow or area that I could draw to show you where the electrons are going, because it's all kind of canceling out here. And that's what I'm trying to say here. So there's not one area where electrons are migrating towards. And these ones do have lots of symmetry. Again, like I said, you hold it in your hand, it kind of looks the same no matter how you're holding the nonpolar molecules. Now, hydrogen bonding. I should point out at this time that if you have a liquid, it's either polar or nonpolar. It's one of the two. It has to be. Hydrogen bonding is like an extra force that polar molecules may or may not have. So we like to say, or I like to say, it's a bonus force between hydrogens and oxygens. So if the molecule you're looking at has hydrogens and oxygens, then it might also have this extra force. If there's no hydrogens and oxygens, it will not have a hydrogen bonding bonus force. It would just be a polar molecule. So here's water that we've discussed, and the dipole's kind of, well, it's not indicated, but we've got our negative end for oxygen and our two positive ends. So what happens when we stick another oxygen near, or another water molecule near this? Well, there are going to be some attractive forces. We know pluses and minuses like to attract. So there's going to be some attractive forces here. And maybe there's another water molecule. So again, you're going to have some attractive forces going on here, and kind of so on. So this is the hydrogen bonding force. It's this purple, it would be these purple lines I'm drawing in. Again, these molecules aren't physically bonded together, they're just attracted to each other. Now, what effect does this have? So here's a practical question. Organize the following compounds from highest boiling point to lowest boiling point based on their intermolecular forces of attraction. That's this polar, nonpolar stuff we've been talking about. So let's take a look at 3 here. We've got oxygen gas. We've got water. And we've got this hydrogen sulfide compound. So if you were to draw out oxygen, it would look like that. And we know about water, and this hydrogen sulfide looks the same. So now we need to make some conclusions. What type of molecules do we have, polar or nonpolar? So if we start with our oxygen one, there's lots of symmetry in this example, or this picture here. It must be a nonpolar molecule. We've discussed water being polar. I've already given away that it also has hydrogen bonding, because that's what we just talked about in the last example. And the H2S, it is just a polar molecule. It does not have the hydrogen bonding, because it doesn't have oxygens. It's got a sulfur here. So now we need to make a conclusion. Well, our nonpolar one, it's got no forces of attraction. It's a very plain molecule. It's going to actually have our lowest boiling point. And if you look this number up, it actually boils at minus 183 degrees Celsius. So it would be a gas at room temperature. So nonpolar ones are always going to be the lowest. Polar ones are going to be much higher because they have attractive forces for each other. So if we had to decide which one's going to be second here, it's going to be the one that is just a polar molecule. And you look it up, it's actually minus 60 degrees Celsius. And we all know water boils at 100 degrees. So it's got the highest boiling point because it has sort of 2 forces of attraction holding it together. There you go.